Okay, so this is the definition of the Dirac delta function, and this is the rather general result of integration that we obtained. And one way to think about this integration result is that the reason why we get f of a is that only the point x is equal to a contributes to the integration, so we'll end up getting the f of a. Now, I want to show you one situation where you must be careful with integrating over the delta function. Okay, so let's imagine doing the following integral. So we have got an integral from 0 to 4. We've got delta of x squared minus 4 times by f of x and dx. So I want to evaluate this integral. Okay. First of all, I want you to try do this integral with what you know so far. So please pause the video now and try to do the integral. Okay, good. Now let's carry on and you can compare what we do to what you did. So first of all, where will all of the contribution to this integral come from? It comes from when x squared is equal to 4, because that's when the delta function, the argument of the delta function vanishes. So this is where we'll get all of the contribution to the integral. And that means when x is equal to plus or minus 2. Now you can see that we're only integrating over positive values of x. So that means that all of the contribution to the integral is from x is equal to plus 2. So the first thing that you might think of doing, and this is perfect, is that we've got an integral from 0 to 4 of delta of x squared minus 4, and then let's put in f of 2 dx. So make sure you're comfortable with why I did that. There is something non-trivial to understand there. I've replaced f of x by f of 2. And then I can again take f of 2 out of the integral. So there's f of 2. There's an integral from 0 to 4, delta of x squared minus 4 dx. So up to now, it has been pretty much what we've seen before. Now is the point where you could fall into a hole, make a mistake. When you want to do this final integral from 0 to 4 delta of x squared minus 4 dx, you might look back to the definition of the delta function and say, well, the integral from b to c of delta of x minus a dx was equal to 1, which told me that the area under the delta function was 1. So you might think that the integral from 0 to 4 delta of x squared minus 4 dx is equal to 1. Well, it isn't. And the way to see that is, in the definition of the delta function, we've got delta of x minus a, so the variable inside the delta function is x, and we're integrating dx. In the integral that we want to do now, the variable inside the delta function is x squared, and we're integrating dx. So the variable inside the delta function is not the same as the integration variable. So it doesn't match our definition. To get things to match, let's change variables. Let's say, let u equal to x squared. U is the variable inside the argument of the delta function. If u is equal to x squared, then we know that du is equal to 2x dx, which is 2 times by the square root of u dx. So we learn that dx is just du over 2 times by the square root of u. So let's just call this I. So what is I equal to now? Well, it's f of 2 times by an integral. When x is 0, u is 0. And when x is 4, u is 16. So it's an integral from 0 to 16. We'll have delta of u minus 4 And now instead of dx, we've got du over 2 times by the square root of u. And you can see that now the entire contribution to the integral comes from the point where u is equal to 4. So I can immediately plug in u is equal to 4. So we've got f of 2. Then we've got 1 over 2 times by the square root of u, the square root of 4. But the square root of 4 is 2. This is just 1 over 2 times 2. And then we've got the integral from 0 to 16 delta of u minus 4 du. And take a look. This now we can use our definition to evaluate, because this is delta of x minus a dx. The variable inside the delta function matches the integration variable, and a lies between b and c. Here we've got delta of u minus 4 du. The u inside the delta function matches the du of the measure, and 4 lies between 0 and 16. So that integral is indeed just 1. So now we get f of 2 times by 1 over 4. And it's this 1 over 4 bit that you would have missed, okay? That came from treating the delta function integral very carefully, and it came because we wanted the integration variable to match what was the variable inside the argument of the delta function. So this is the subtlety with dealing with integration over delta functions. What we want to do now is to derive a general rule that will tell us how to deal with this subtlety. That's what we'll do next.